Okay, hi everyone. I'm Yuto, and today I'll be talking about my postgraduate thesis research, which investigates the reinforcement learning integration in architectural design. So, my name is Yuto Ikeda. I studied architecture in Bartlett UCL and now working as a Part 2 architecture assistant at Foster and Partners. And my specialty and interest is advanced computational design with procedural systems, looking at themes such as performative design, organic form generation, and bioreceptivity. So to begin with, architecture design has been benefiting from computational tools for decades, from computer-aided design to parametric design and BIM information modeling. Recently, with technologies such as performance-based optimizations, the design has been becoming smarter. We now see the digitalization of architecture reasoning, with which the design decisions are made according to objective metrics like environmental performance, rather than subjective narratives such as aesthetic. And with the recent surge in the interest in artificial intelligence, this field has been seen as the next paradigm in the computational design tools too. There are already many researches and early implementations of this with a focus on predictive simulations, image generations, and form derivation, like we've seen with infrared city with Orna in the morning. On the other hand, the AI tool integration in one of the core tasks for architects, which is iterative design study, remains relatively limited. This is because as the task becomes more generic, creative, and three-dimensional, the existing tools start to become restricted. Some of the available tools for the iterative design and generative design study includes the likes of Forma, Finch, or Delph. However, they are practically limited to conventional building designs due to their algorithmic characteristics, which is assumed to be based on supervised learning, unsupervised learning, and genetic algorithms. All of these need either existing datasets or logic sets to train on, and therefore the output tends to be a derivative version of a conventional design. So considering these limitations of the existing tools, one type of machine learning with a prospect of performing in generic and creative design studies is reinforcement learning, or RL. In reinforcement learning, the agent learns through interaction with the environment without any precedence data. The ability in heuristic solution search born from this and its methodological similarities to the iterative design development are the technical advantages of RL in design augmentation. So my research explored the possibility of RL implementation in generic architectural design with the focus on environmental performance optimization at the massing stage. So the research hypothesis asked if RL can effectively optimize architectural environmental performance in preliminary design explorations. Now, the methodology to examine this hypothesis involves the 3D software Houdini and the machine learning library of PyTorch. The software was chosen for its ability to procedurally create custom environments, integrate Python scripting, and utilize built-in timeframes. The technical strategy of the agent training and inference is achieved with the creation of a reinforcement learning agent with PyTorch and the custom environment in a Houdini file. The agent is trained in a Python script object node in Houdini, outputting numerical data as its action. This overrides the parameters of the procedural modeling system in a geometry node, which hosts the custom environment. In the environment, a low-fidelity massing representation is created based on the action output and evaluated with environmental simulation. The results of these operations are read by the agent as the numerical data back in the Python script node. And in each of these procedures, an operator is developed for the following functions. So for custom environment, which is for state observation, action execution, reward calculation, state update, and episode recording, agent training for module import and algorithm selection, neural network structure, Houdini environment operation, saving trained agent, and training loop. And finally, agent inference for neural network replication, agent selection, and environment operation. For the custom environment, Houdini geometry nodes are used to represent the spatial conditions. The flowchart shows how each of the functions are connected in the environment, directly reflecting the node structure of the Houdini script that you can see on the right. And in order to achieve this proof of concept RL integration demonstration, the geometric forms are represented with low fidelity pixels and voxels. In this way, the computational load is limited for the research, while linear scalability is simply shown by a test with two different resolutions. The state of the environment is communicated to the agent with a selection of condition indicators shown here. This includes site mapping, mass indication, neighbor count, neighbor indication, solar count, shade count, and mass count. Each of them are translated into numerical data, like you can see here, for the RL agent input. Similarly, the action output is communicated back to the environment via numerical representation. In this research, I have developed two action methods, which are rolling and targeting. In summary, the rolling goes over all the available space and determines whether to place a mass or not, while the targeting specifies the location to place for the mass for every action step. The reward value is then calculated with these methods in order to incentivize the mass deployment with optimized environmental performance. This is a selected combination of site boundary, mass count, average solar gain, light surface count, shade surface count, mass overlap, and surface overlap. Each of them are either positive reward or negative reward, depending how desirable they are. With the training environment set up, the script then chooses the type of RL method, which dictates how the policy is adjusted. Throughout the development of the research, the simpler tabular method of Q-learning and its developed version or deep learning version of deep Q-learning is used for early proof of concept experiments, while a more advanced algorithm or PPO is employed for the later stages. Now, these operators are constructed using Python scripting. The following slides show each section of an exemplary code for RL agent training. First, the optimization algorithm is defined. The presented is an example for a deep Q-learning method. Then the neural network structure is created according to the input and output of the environment. For the PPO, two neural networks are constructed for each of the actor and critic of the agent. And next, a series of functions is defined to manipulate and communicate with a custom environment inside Houdini. So the functions are categorized into reading and writing of the Houdini parameters and the calculation done through a Houdini geometry node. In each specific operations, the node and the parameter can be specified using these functions. And these are the integrated in a complete training loop script for the agent training. This script shows a training loop for a deep Q-learning algorithm. In principle, the training process contains the steps of 1, reading the state, 2, deriving and outputting the action based on the existing policy, 3, reading the new state and reward value, and 4, adjusting the policy. And this one is for the PPO algorithm. The benefit of the PyTorch machine learning library employment is evident here with the simple and straightforward coding. Finally, the RL agent is saved based on the episode with the best reward value in the last 5% of the training. This is to avoid the possibility of saving the premature configuration, which stochastically achieved high reward value at the exploration stage. And the performance of the RL implementation is evaluated on reward transition and inference validation. So the reward transition parameters consist of best episode reward, initial learning trend, final rolling average, and final coefficient of variation. Therefore, these parameters determine the effective learning of the agent, while the inference verifies the efficacy of the training itself. So based on the methodology outlined, I set up 3 levels of research studies with increased complexity to gradually develop and test the RL models. The first study, Study A, was a proof of concept model with the aim of site recognition in a two-dimensional map. Then study B developed a 3D model for solar radiation gain optimization over voxel massing, directly investigating the hypothesis. Finally, in study C, a multiple objective optimization model was built to further reinforce the possibility of allo integration within architectural design. Now, the following slides will show the results of these research studies. First, in study A, I created 20 different variations of RL models to test the combinations of variables such as resolution, action method, reward calculation, algorithm type, and neural network structure. The diagram on the right shows the tested configurations for each of the variations in the study. So the presented graphs show the reward value transitions over the training episodes for each variation. The most evident observation here is that the rolling action method, which is shown in the left graph, has clear advantage over the variations with targeting method, which is shown in the right graph. While there are a couple of curves showing stable learning with the rolling method, the ones with the targeting method show immediate failure or stalling around 0, even over a significantly larger number of episodes. The recorded geometries of the episodes also support this observation. Here, each frame represents the terminating state of one episode in two of the rolling method models at different resolution. Overtraining, you can see that the agent action converges to the mass placement within the site, successfully showing the site recognition by the agent. So building on this, in study B, I predominantly employed PPO algorithm with fixed resolution, neural network structure, and action method, and investigated further into the state input and reward engineering. The result table on the right shows a successful training with the fourth variation of PU3. In the reward transition diagram, or the graph, this configuration has the most stable and positive learning trend. This is further validated with the reward value plotting on the right, where the yellow points of the variation PU3 have the strongest convergence closest to the Pareto frontier. So in comparison to the failed training on the left, which only sparsely places volumes in sporadic fashion, the successful model shown on the right managed to find the optimal solution and start to aggregate masses on one side of the site to maximize the solar radiation gain. So based on this, multiple configurations are created and tested to achieve multi-objective optimizations in study C, with solar radiation gain maximization and surface area maximization. Here, I will present one of the successful models, which used these values for the environment and training settings. You can see here, as the optimization task becomes a bit more complex, the dimensions of the state input, reward calculation, and accordingly, as a result, the neural network complexity increases exponentially. The reward transition of this model depicts a stable improvement of performance during the training. The global reward value in orange shows the general learning, which improves significantly in the first half of the training and plateaus, while the average solar radiation gain and relative surface area keep increasing gradually. In the three-dimensional plotting of the performance values, it is also clear that the agent started to maximize those two objects throughout the training. Another significant observation in the last study, which is study C, is that as I introduced another performance objective, the resulting geometry became more dependent on the stochastic exploration of the initial mass placement. In the training video, you can see that the placed mass configurations do not converge to one solution, such seen in earlier studies, and instead adapt to what is placed on the previous steps in the episode. This is clear in the inference examples too, where the study B agent places the masses as predicted based on the training results. The study C agent utilizes some randomness in the inference to derive the mass aggregation. This is assumed to be due to the interdependentness of the state and reward calculations, where the already deployed voxels influence the future placement of the masses. Nevertheless, it is confirmed that the result is not completely stochastic and remains effective, as the performance evaluation proves for the training and inference. The trained agent can therefore be used for architectural applications, such as this design concept, where the massing volumes are aggregated autonomously on the site by the agent. Here, the concept utilizes the optimized solar radiation gain and surface areas of the building mass to provide daylight for residents while accommodating biological growth on the structure simultaneously. Now, based on the methodology and its results, the presented hypothesis is validated through the research studies. First, a successful machine learning integration within the software Houdini is achieved with the use of PyTorch library. Then the custom reinforcement learning model produced autonomous massing with the optimized environmental performances, confirming the potential of RL enhanced architectural design. Additionally, the research developed multi-objective optimization with RL, further expanding the possibility of the methodology. While on the other hand, the research also recognizes some limitations, especially with the hyperparameters tuning and the detail variables associated with them. That being said, the primary unexamined variables include site boundary calculation types, reward calculation types, and activation functions. While these are expected to alter the learning process and performance, the effectiveness of RL implementation for architectural design is verified nevertheless by the presented results, as well as their minor variations. Finally, I want to mention the future prospect of the topic based on this research, which includes scaling in both resolution and size, continuous representation of geometries and actions, additional design objectives, and specializations. Although very primitive, as this research produced fundamentally promising results, I believe many exciting adaptations can be developed with RL augmentation in the industry. Thank you so much. And you can also find the original thesis paper as well as the assets, including scripts, models, and videos in the GitHub repo here. Thank you.